Hello and welcome to the CSSPP Googun presentation.
I'm Todd Paboni.
I'm Natalie Leptrell.
We have Todd Nabani, Patrick Mogianesi, Lisa McPhillips, and I'm Owen Bosley, and we're the Googun team. Our mission is to simulate realistic human mucus production and cough behavior as a stress test harness for respiratory medical prototypes that are mounted at the end of an endotracheal tube. Our client, Certus Critical Care Incorporated, or 3CI, is developing prototypes that have sensors located near the end of an endotracheal tube, shown here in green. The image on the right depicts an intubated patient connected to a ventilator. The patient produces mucus that is driven up the endotracheal tube as they breathe and cough. This mucus may gather at the end of the endotracheal tube in the area shown in red. Our goal is to simulate the environment created by the patient at the sensor access point. 3CI would like to know how their electronics may be affected by this unique environment and have tasked us to build a simulation device, which we have named the Googun. 3CI specified a list of requirements that our solution must meet. The primary requirements detail the functions that the system must perform, while the mucus and cough specifications detail performance constraints for the first requirement. The primary requirements that the client gave to us were that the system must simulate human mucus secretion and cough production. Additionally, it must be able to push the artificial mucus towards 3CI's sensor access point, and that mucus must be injectable into an endotracheal tube. Additionally, the test parameters must be controllable via the PC GUI by the user, and the system must be able to autonomously operate for at least 1 hour continuously. Limitations on the mucus secretion by the Googun include specifications about resolution, accuracy, and speed, and the cough limitations have specifications regarding volume, pressure, and accuracy. We synthesize these requirements into 2 modules: the mucus injector module, or MIM, and the mucus propulsion module, or MPM. These modules are controlled by a microcontroller that uses parameters sent from the user interface on the PC. The user can set test parameters on the GUI and send them to the microcontroller, which uses these parameters to determine how to operate the modules. The mucus injector module injects controlled volumes of artificial mucus into the endotracheal tube using a stepper motor controlled syringe pump. This simulates the secretion of mucus by a patient. The mucus propulsion module propels this injected mucus towards the device being tested. This is done by using an electronically controlled valve to expel controlled volumes of air from a regulated pressure tank. This simulates the propulsion of mucus up the endotracheal tube via coughing. Moving forward, we will expand on these modules, beginning with the mucus injector module.
Natalie, you're muted.
Natalie, is your mic on?
Natalie.
I think she might be frozen.
So the mucus injector module is a stepper motor driven syringe pump. This means the stepper motor, shown here, rotates the threaded rod, which drives the moving block. This pushes the syringe plunger, which injects the mucus out of the mucus output, or retracts the syringe plunger, which pulls mucus from the mucus reservoir input. This design is composed of 8 custom 3D printed parts and the 19 off-the-shelf parts. The MIM must meet 4 requirements. It must first be high resolution. This means the Googun must be able to inject at most 600 microliters per step of the stepper motor. Our final design has a resolution of about 4 microliters per step. The second criterion says that the amount of mucus injected must be accurate to the amount set by the user within a 3% error. This ensures that the data that 3CI collects using the Googun is reliable enough to serve as testing equipment. Our design has a 0.1% error. The Googun must also simulate the rate of human mucus expulsion. This means it must be able to inject at a minimum of 2 milliliters per minute. Our design can accurately inject at approximately 11 milliliters per minute. Lastly, the Googun must be able to inject artificial mucus into an endotracheal tube. An endotracheal tube is made of soft and flexible PVC plastic, and so we must solve this problem by attaching a needle to the end of the MIM. This needle will be able to easily pierce the endotracheal tube. The reason that it is marked conditionally true is that we did not obtain an endotracheal tube, so this requirement has not been formally tested. The mucus propulsion module is a pressure-regulated air compressor moderated by a solenoid valve. The MPM utilizes a pressurized air source whose output is connected to the eastern port of the pressure regulator, shown here. The pressure regulator regulates the supply output to the range of 0 to 5 psi. There are 3 output ports on the regulator with connections to an analog pressure gauge, an electronic pressure sensor, and the solenoid valve. The western port on the regulator allows the air to flow from the regulator to the valve, which opens or closes to control airflow. The air output volume of the MPM is determined by the pressure settings at the regulator and the open time of the valve. This design consists of 1 custom 3D printed part and 9 off-the-shelf parts. The MPM has 4 system-specific requirements. First, the MPM must be able to simulate the air volume of a human cough, which was specified to be larger than 500 milliliters per expulsion. Our solution can expel air at volumes up to 740 milliliters per expulsion. The second requirement states that the air output volume must be accurate within 3% of the user-specified volume. This ensures that the data 3CI collects using the Googun is reliable enough to serve as testing equipment. Due to time constraints, however, we were unable to fulfill this requirement, and it is thus marked incomplete. The third requirement states that the mucus propulsion pressure simulates a range of human cough pressures. The client specified a range of 40 to 170 centimeters of H2O. Our system can operate between 35 and 190 centimeters of H2O. The final requirement states that the pressure readings from the pressure sensor are accurate within 3% of the value set by the user. Again, this ensures the Googun is reliable enough to serve as testing equipment. The sensor in our system is accurate within 2% of the user set value.
To reiterate, the Googun must be able to take test parameters from the user. To accomplish this, we developed a graphical interface that allows the user to control the Googun system from their personal computer. The Googun system is controlled through parameters shown here, where they're sent to the microcontroller, where the microcontroller controls the MIM and MPM modules based on those parameters. In addition to controlling the system, the feedback packets are also sent back to the GUI, where statuses of the system are reported back to the user, such as the MPM pressure levels. Additionally, the GUI tracks the experiment history by keeping a log of experiment parameters sent to the microcontroller. These are displayed in the automated log window shown here. This information is also logged in an external file as requested by the client. Overall, this GUI accomplishes what we set out to do by allowing the user to provide parameters to the microcontroller and the system and update the GUI based on successful transactions.
As visualized here, these 4 elements make up the Googun. However, due to COVID-19 and social distancing policy, we were unable to integrate these systems together. Therefore, we did not meet the minimum autonomous runtime and endotracheal tube integration requirements. Despite this, the setback gave us the opportunity to have more time to refine the individual modules. This slide shows photos of the finished mucus injector module and mucus propulsion module and visualizes how they would have been integrated. If we had had more time to work on the project, there are a few more things we would have liked to have completed. The first thing is that we would have liked to have fully integrated the mucus injector module and mucus propulsion module together. Integration would allow for us to test with a minimum autonomous runtime and endotracheal tube functionality requirements. Second, we would like to develop an airway receiver module, which would allow our system to interface with the ventilator and do system testing with it. We initially had access to a ventilator, but it was donated to a hospital due to the COVID-19 pandemic. And lastly, we would have wanted to improve the GUI such that the Googun system could be manually controlled and calibrated directly from the GUI. Thank you for your time, and we'll now open up the floor for questions.
Thank you very much, Googun team. Thank you for the presentation. Actually, I have a question for you. Maybe you skirted artfully around my question, but what is the mucus made of?
The mucus is an artificial recipe that we've looked into. So it's mainly made up of water and a little bit of guar gum.
Of what?
Guar gum, it's a industrial chemical.
I see. So if the pandemic hadn't taken its toll, what would be sort of the next step or the next steps that you would want to take?
So if we had time to meet in person, without the social distancing policies, we would have liked to have gotten the systems that were developed separately in separate locations together to test all of them together and use the GUI to send commands to each of the systems and test that it can run autonomously, basically.
Mm-hmm. And what would you say is your biggest worry at this point? Which part are you least confident in?
The mucus propulsion module sort of got delayed. The accuracy requirement was obviously incomplete, and unfortunately, we just didn't have the time to complete it. We really would have liked to have gotten all of the requirements for each of the individual modules completed so that when we do come together, everything is already set up to integrate.
Mm-hmm. All right. Thank you very much.
Thank you.
Great work. I hope it will proceed in the future.